Okay, in this video what we're going to do is talk a little bit about Gauss's law, which is a tool that we're going to use for calculating the electric field. Up till now what we've done is we've set up the total electric field as the sum of a bunch of little electric fields due to small bits of charge, or what we've done most recently is integrating over the charge to find the total electric field. This works in a lot of cases, but it can be mathematically a little taxing. And so there are some special tools that we can use when we have certain kinds of geometry, certain kinds of shapes, and certain kinds of symmetries, which is certain kinds of shapes that are similar in some sense. And we'll talk a little bit about that in a moment. But one way to sort of motivate this is to think about just the point charge. So we have some positive point charge here. And that positive point charge produces an electric field that points radially outward everywhere. So if we were to draw it like this, it would point sort of outward everywhere in space. And if we're at the same distance from the point charge on, say, a sphere that surrounds the point charge, these electric field vectors are exactly the same length. So one thing that you know about the electric field, the magnitude of it anyway, is that the total electric field from a point charge looks like that, right? And what happens is it gets smaller as 1 over r squared. So what we say in physics is often that it's inversely proportional to r squared. The other thing that we can notice is actually if we think about this whole bubble that encapsulates this positive charge, that bubble is a spherical surface. And that spherical surface has a surface area that looks like 4 pi r squared. That is, it's directly proportional to r squared. So this suggests that some sort of thing that is like the multiplication of the magnitude of the electric field and the magnitude of this surface area varies like 1 over r squared times r squared, which is a constant. That is, that the product of this electric field and the product of the surface area of this bubble, in some sense, doesn't change with distance away from the charge itself. And that's kind of an important geometric idea that we're going to use to develop Gauss's law. This thing that we're going to talk about and we'll formalize in the next video is called the electric flux. And it tells us about sort of how much electric field is penetrating through an invisible surface that we're going to draw around this. So the fact that we can sort of construct a quantity that has this constancy to it, the fact that the electric field varies like 1 over r squared and the surface area varies like r squared, gives us this sort of motivation to investigate this new quantity that we're going to call flux.